In the shadows of everyday life, some of the most powerful global systems are not found in financial markets, military alliances, or digital surveillance networks. They are hidden in plain sight, in kitchens, in walls, behind power sockets that millions of people use without a second thought. One of the most revealing examples of this invisible infrastructure divide is not about wealth or politics, but about something far more ordinary: boiling water. In Sydney, an electric kettle clicks on in the early morning silence. 90 seconds later, steam begins to rise. In Los Angeles, a similar kettle hums under the same expectation, but the wait stretches closer to 3 minutes, sometimes more. The difference is not the kettle. It is not the water. It is not even the user. It is the grid. And that gap between 90 seconds and 180 seconds opens a window into a 140-year-old technological decision that still shapes daily life across continents. To understand why, we have to step back into the origins of electrical civilization itself. The modern comparison between Australian and American kettles begins with a simple but striking observation. In Australia, boiling 1 litre of water in an electric kettle takes roughly 90 seconds, while in the United States, the same task takes nearly 3 minutes under typical household constraints. For travellers moving between these two systems, the difference is immediately noticeable. Australians arriving in American homes often perform an instinctive ritual, plugging in a kettle, waiting, watching, and gradually realising that something feels wrong. The speed they took for granted is gone. In its place is a slower rhythm that quietly reshapes expectations. Many eventually abandon the kettle altogether, defaulting to microwaves or stovetop boiling. It is not dramatic enough to be shocking, but it is persistent enough to be remembered. This is not a cultural preference. It is an engineering outcome.
At the core of this divergence is a relationship between voltage, current, and power. Electrical power is measured in watts, and watts are the product of volts and amps. This simple equation hides a structural truth about national infrastructure. In Australia, standard household outlets deliver approximately 240 volts. In the United States, the standard is 120 volts. That difference alone determines how much power a kettle can draw from the grid.
In practical terms, an Australian electric kettle can typically operate at around 2,400 to 3,000 watts. A standard American kettle, constrained by household circuit limits, usually operates at about 1,200 to 1,500 watts. This is not because American engineers are less capable, nor because appliances are fundamentally different. It is because the electrical pressure available at the socket is lower. Engineers often use a simple metaphor to explain this. Imagine 2 garden hoses filling the same bucket. If both hoses are identical in width, but one is under higher pressure, it will fill the bucket faster. Voltage is that pressure. Current is the flow. Power is the total energy delivered. In Australia, the hose is pressurised at roughly double the force. In the United States, the system runs at half that pressure for general household circuits, and so the kettle waits. But this technical difference is not an accident of modern engineering. It is the result of a historical decision made at the dawn of electrification, when the rules of the modern world were still being written in real time. To understand the origins of the American system, we must return to New York City in 1882. In Lower Manhattan, Thomas Edison opened the Pearl Street Station, one of the first central power stations in the world. It marked the beginning of widespread electrical distribution in urban environments. But Edison's system was built around a very specific constraint: incandescent light bulbs. At the time, electrical engineering was not yet a mature science. Edison's priority was not efficiency across a national grid, but commercial viability. His incandescent bulbs required a stable voltage that would keep filaments glowing without burning out too quickly. After experimentation,
he settled on approximately 110 volts as a workable standard. It was a compromise between brightness, safety, and filament lifespan. This decision, made for the sake of light bulbs, became foundational.
As electrical systems expanded across American cities, Edison's standards spread with them. Competing systems did exist, most notably those supported by Nikola Tesla and George Westinghouse, who advocated alternating current systems, capable of transmitting power over longer distances more efficiently. This conflict became known as the War of Currents, a defining technological battle of the late 19th century. Tesla's AC system eventually won in terms of infrastructure design. It was more efficient, more scalable, and more suitable for large national grids. But Edison's voltage standard had already been physically embedded into the urban fabric of the United States. Light sockets, appliances, wiring conventions, and manufacturing standards were all aligned around roughly 110 volts. This created what engineers now call path dependence. Once a system reaches a certain scale, changing it becomes exponentially more expensive than maintaining it, even if a superior alternative exists. By the time electrical engineers fully recognised the long-term advantages of higher voltage household distribution, reduced transmission losses, thinner wiring requirements, and improved efficiency, the United States was already locked into its initial configuration. Millions of homes, factories, and cities were built around a system that could not be easily redesigned without dismantling entire layers of infrastructure. Meanwhile, other countries were beginning to electrify later. Australia, Great Britain, much of Europe, and parts of Asia were building their electrical systems in an era when the limitations of early low-voltage distribution were already well understood. Engineers designing these systems were not constrained by Edison's early choices. Instead, they adopted higher voltage household standards, typically around 220 to 240 volts, which allowed for more efficient energy transmission and better performance for heavy household appliances. This divergence was not ideological, it was chronological. Countries that built later inherited better information. Countries that built earlier inherited physical constraints. And once these systems were established, the cost of convergence became prohibitive. Converting an entire national grid from 120 volts to 240 volts is not a matter of replacing sockets. It involves rewiring homes, upgrading appliances, modifying industrial systems, and replacing millions of transformers. The estimated cost runs into trillions of dollars, with decades of disruption. As a result, the United States remains structurally tied to a decision made in 1882. Yet the irony of this system is more complex than it first appears, because American homes do, in fact, contain 240-volt power. Inside the breaker box, the hidden control centre of residential electricity, split-phase systems deliver higher voltage lines designed for heavy-duty appliances. Electric dryers, ovens, and air conditioning units routinely operate at 240 volts. The infrastructure exists. The capability is present, but access is intentionally segmented. The kitchen counter, however, is treated differently. Standard outlets remain locked at 120 volts, limiting the performance of everyday appliances like kettles, toasters, and coffee machines. In effect, the American home contains two tiers of electricity: a high-power industrial tier reserved for large appliances, and a lower-power domestic tier for everything else. This creates a subtle but persistent hierarchy in appliance design. In Australia, the electric kettle is not a specialised device, it is essential infrastructure. In the United States, it is optional, often redundant, competing with drip coffee machines or stovetop methods that bypass the need for high-wattage rapid boiling at the counter level. Over time, this has shaped behaviour. In countries with 240-volt systems, the electric kettle became central to daily life. In the United Kingdom and Australia, it is so essential that grid operators have historically monitored TV pickup events, Moments when television broadcasts end or commercial breaks occur and millions of kettles switch on simultaneously. The sudden surge in demand is so predictable that it becomes part of national load management strategies. In contrast, the United States never developed such a kettle-centric culture. Instead, coffee culture evolved around drip machines, espresso systems, and stovetop methods that distribute heating differently. The kettle remains present, but not dominant. This is not simply about preference, it is about what the infrastructure encourages.
When energy is abundant at the socket, behaviour accelerates. When it is constrained, behaviour adapts around alternatives. The difference between a 90-second boil and a 180-second wait does not appear significant in isolation, but across millions of households, repeated multiple times per day, it reflects a deeper divergence in how time, convenience, and domestic efficiency are structured. Ultimately, the contrast between Australian and American kettles is not about appliances at all. It is about historical inertia. The reason an Australian can prepare tea in under 2 minutes, while an American waits significantly longer, is not because of modern inefficiency, but because of a decision made in the early days of electrical experimentation, when engineers were optimising for incandescent lightbulbs, not global household ecosystems. That decision, embedded into infrastructure, survived wars of standards, survived technological revolutions, and survived the transition into the digital age.
And today, it still determines how long it takes to boil water. It is a quiet reminder that modern life is not built on present-day choices alone. It is layered on top of older systems, older compromises, and older assumptions that continue to shape reality long after their origins have been forgotten. The grid does not remember why it was designed the way it was, but every morning, in every kitchen, it continues to enforce the decision.